The topic of this video is low-rank decompositions of matrices. This is a very important concept in machine learning. So our objectives are to define what we mean by a low-rank decomposition. It's sometimes also called a matrix factorization, and we'll explore several applications. And we've seen by now that matrices can represent many types of information. We've looked at features in classification or modeling. We've looked at users' ratings of things like movies or products. We can also use matrices to represent collections of documents. For example, one approach is to use the so-called bag of words model, where you just count the number of occurrences of each word in a particular document and put those counts in a vector. So you're ignoring the relationships between words, you're simply counting the words that are in the document. For example, if I have the sentence, "Apple trees blossom in May," I can count the frequency of the words in that sentence. So agency does not occur in that sentence. It has zero frequency. Apple occurs once. Blossom occurs once. Car does not occur. Currency does not occur. May occurs. And politics and road do not occur. And tree does occur. If I have a dictionary of words that I'm considering, then I can count the frequency of each word in a document and represent that document with that vector. And if I stack a bunch of those vectors as columns into a matrix, I have what's called a term document matrix. So the terms go down the rows, that's the count of each term or word, and then across the columns I have different documents. And by studying the structure of this matrix, we can infer things about the relationships between documents, similarities, we can perform queries to look for certain terms, and so on. Now, low-rank decompositions of such matrices emphasize patterns, and that's the main purpose of these, is to identify dominant patterns that we can use in our subsequent machine learning. So let's take an n by m matrix A, so it says n rows and m columns. A low-rank decomposition represents that matrix as the product of an n by p matrix T and a p by m matrix W transpose. In general, p is going to be less than n and p is going to be less than m. Oftentimes, p will be significantly less than both n and m. Now, if the rank of T and the rank of W are both p, then the rank of this product T times W transpose is also P. And in general, A could be rank as large as the minimum of N or M, so P, being much smaller than those, represents a low rank approximation or a low rank decomposition of the matrix A. So we're going to define the matrix T in terms of its columns, T1, T2 through TP, and a matrix W in terms of its column, W1 through WP. And then T times W transpose can be written as the outer product of a series of column patterns associated with the T's times a series of row patterns associated with the rows of W transpose. So when I do this multiplication, I have T1 times W1 transpose plus T2 times W2 transpose and so on. And I see that I can write this as a sum of I equals 1 to P Ti Wi transpose, and each of these products is a rank 1 matrix because it's a product of an n-dimensional column times an m-dimensional row vector. And that results in an n by m matrix. In this form, we're writing A as a sum of these rank 1 pattern matrices. Now, a really important question is how do you find good patterns, T and W, to do this kind of low-rank decomposition? And there are multiple approaches to this problem, 3 of which I've listed here. So one approach is to say that you want to find the T and the W transpose that are rank P so that this product, TW transpose, is the closest possible to the matrix A in the sense of some norm. And we'll look at a specific norm and find that this leads us to the topic of singular value decomposition of the matrix A. Yet another approach is to factor A in terms of a product of matrices T and W transpose where all the elements of these matrices are non-negative. This is a so-called non-negative matrix factorization, and is very useful in certain problems where A contains positive entries, such as the term document matrix or a ratings matrix. Yet a third approach is to restrict the matrix W transpose so that each column contains all zeros but has a single 1. So let's suppose there's a 1 in the kth row of W transpose. Well, what that's going to do is pick out the kth column of T. Therefore, we're approximating each column of A in this case by a particular column of T. And this is a so-called clustering problem. So let's explain this clustering idea in a little more detail. So suppose I have a matrix whose columns are A sub I, so the A1, A2, A3, and so on up to A sub M. And I'm going to approximate that matrix as a matrix T, which in this example we'll assume T has 3 columns. In clustering, the matrix W transpose has a single 1 in each column and the rest elements are zeros. So for example, I might have 0, 1, 0, and if I multiply these out, this tells me that the first column, A1, is equal to 0 times T1 plus T2 plus 0 times T3. So A1 is being approximated by T2. Similarly, if I go down here to AM, 0 times T1 plus 1 times T2 plus 0 times T3, in other words, A sub M is also being approximated by the column T2. And similarly, we can look at the other columns, and the way I have this set up in this example, the second column, A2, is being approximated by T1, as is the third column, because there's 1s in both of these cases. And then the fourth column of the matrix A, A4, is being approximated by T3, and so on. If I draw an example of this in 2 dimensions, so this would be n equals 2, and we'll assume that there are P equals 3 clusters, like I've drawn here with T1, T2, and T3. In this case, I've chosen M to be 45. You can see that this data maybe could be represented by 3 clusters. One here that's T2, another that's clustered around T1, and a third that's clustered around T3. So what we'd like to do is take a matrix of measurements, all 45 data points that are represented in this 2-dimensional problem, and then we'd like to group the ones that are similar. In other words, assign cluster centers to those, and that could be representing similar documents, grouping customers that have similar preferences, grouping products that have similar attributes, and so on. Now, there are a lot of different algorithms for doing this kind of clustering. One is the k-means algorithm, and that's something that we'll look at in detail in a subsequent lecture. Now, something else you can do with these low-rank models is complete missing data. For example, suppose we have these 5 movies: Star Trek, Pride and Prejudice, The Martian, Sense and Sensibility, The Empire Strikes Back, and Jill has watched 4 of those, and we'd like to make a prediction what her rating is going to be for the 5th one, The Empire Strikes Back. We're going to assume a model that our ratings are given by the sum of 2 terms: an average term, which has 1s in all of the different elements, and then we're going to assume that people have different preferences for science fiction movies versus romance movies. So we've put 1s here in our second column of T in the positions corresponding to the science fiction movies, and we've put -1s in the positions corresponding to the romance movies. So if someone preferred romance movies over science fiction movies, W2 would be negative, and that would increase their ratings of the romance movies relative to the science fiction movies. So in this case, we're assuming we know these 2 patterns and that our overall ratings matrix has these 2 columns for T. So what we can do in this case is use these 4 movies that Jill has rated to find the W1 and W2, and I've set that up here as a least squares problem, and you find that W1 is 5.5, which happens to be the average of these 4 ratings, and W2 is 2. Well, once we have W1 and W2, we can then predict the ratings, and we'll call that A hat, using W1 and W2 and these low-rank bases, T1 and T2, for this 5-dimensional space representing ratings. we find that we predict Jill's ratings to be 7.5, 3.5, 7.5, 3.5, and 7.5. Thus, we would predict that Jill's probably going to like the science fiction movie The Empire Strikes Back. Now, you'll note in this case, each of these categories has just been replaced by the average rating for their category in this prediction. And that's because we used only 2 taste profiles or basis vectors to represent these ratings. In general, if one had a more complex problem with a lot more data, you would end up with more diversity in your ratings. Now, another benefit of this low-rank approximation is that by relying on the dominant patterns, we can mitigate the impact of noise. For example, let's suppose I'm collecting features for a classification problem or a modeling problem, and there's noise present. So I have underlying features that I can't measure, which have strong patterns in them, and then I have this noise which really doesn't have any dominant pattern. So if that's my measured data, A sub m is noisy, and I approximate this with a low-rank model, say T times W transpose, I can choose T and W transpose in such a way that this low-rank model ends up being closer to the true features in AT than to the measured data A sub m, because our patterns can, represented by T and W, will clue in on the strong patterns in AT and not be influenced very much by the lack of structure that's present in the noise data. So then I can set up, say, a low-rank classification problem or a low-rank modeling problem by replacing A sub m, my measured noisy data, with my low-rank model. We have the least squares problem where we're trying to solve A sub m hat times W is equal to D. Substitute AM hat in terms of its low-rank decomposition. We have T times capital W transpose times lowercase w is equal to D. And we still want to solve this as a least squares problem. One thing that we observe is that since W transpose is a known matrix, the product of capital W transpose and our m-dimensional vector lowercase w is actually a p-dimensional vector. We'll call that W prime. So I can restructure this problem to solve for W prime, and my least squares problem becomes T times W prime being equal to D. And we can solve that problem using straightforward methods of least squares. In fact, if the columns of T are orthonormal, as sometimes is the case, then this is a particularly simple least squares problem to solve. Now, these rows of the matrix T, I can think about those as transformed lower dimensional features. So if I had the original rows in A sub m, let's say the rows of that matrix were features xi transpose, then these transformed features, we'll call those xi prime transpose, and you can show that the relationship between the transformed features xi prime transpose and the original feature xi is through W times the quantity W transpose W inverse, where again, this is the uppercase W, the matrix, in our low-rank approximation. So when I have a new feature, say X transpose, that I want to classify after I've solved this problem to learn my classifier weights, then I would first compute X prime transpose by multiplying X transpose on the right with capital W times the quantity capital W transpose times capital W inverse. And once I have these transformed features xi prime that correspond to the rows of T, then I can do my classifier as D hat is the sign of X prime transpose times W prime. And this approach here adopts many of the attributes that we looked at earlier when we studied classification using orthonormal bases. So the use of low-rank approximations to matrices is pervasive throughout machine learning, and it's a very powerful tool. We'll be exploring this topic more deeply over the coming lectures.